System impedance ratio. What is system impedance ratio? What is the need to understand system impedance ratio? What are the benefits of understanding system impedance ratio for a protection engineer? Let us say your relay tripped for a fault. That's what it is meant to be. But if a fault occurs and the relay is not tripping and you find all the settings to be perfect, then what is the issue? System impedance ratio helps us to understand to a certain extent on why this has occurred. To understand further, in this video we are going to discuss about the formula for system impedance ratio, some examples to understand how this formula is working, and then from the results we are going to conclude how the system impedance ratio is going to help a protection engineer. So let's move on. System impedance ratio is defined as source impedance divided by line impedance. Let's take a system as shown, a generator connected to a transmission line. Let us assume 11 kV. The left hand side we can call it as system 1, and in the right hand side let's assume it as system 2. So in system 1 we consider the source impedance as 2 ohms and the line impedance as 10 ohms, whereas in system 2 we consider the source as 10 ohms and the line as 2 ohms. In both the cases, the voltage of source is assumed as V1 and the line voltage as V2. Now let's calculate the system impedance ratio. SIR is equal to source impedance divided by line impedance, that is 2 by 10, results in 0.2, and here it is 10 by 2, which is 5. Now let us assume a fault exactly at the midpoint of the line. This is for ease of calculation. We are assuming the fault at the midpoint. Now what happens to the line impedance? The current, that is the fault current, flows only in the least resistance path. Therefore, the fault resistance would be 50% of the total line resistance. So the total resistance of the system can be calculated as the source impedance added to 50% of the line impedance. Therefore, 2 added with 50% of line impedance, that is 5, results in 7 ohms. In second case, it is 10 ohms added with 50% of 2 ohms, that is 1, which results in 11 ohms. Now let's calculate the fault current using Ohm's law. So V by R, here it is 11,000 volt divided by 7 ohms, results in 1.57 kilo amps. The second case, it is 11,000 divided by 11, results in 1 kilo amps. Let us also calculate the V1 and V2 values using V equal to IR. So by substitution we get 3.143 kV as source voltage V1 and V2 as 7.857 kV. In system 2, using the same formula, when we calculate V1 and V2, we get 10 kV and 1 kV respectively. This is the calculation for system impedance ratio. So from this, what do we conclude? When you look at the fault current, in case 1 it is 1.57 kilo amps, whereas in case 2 it is 1 kilo amps. So whenever we see a source which is capable of feeding a huge amount of current to the fault, it is called as a strong source. A strong source is one which is capable of feeding any amount of fault current. And what is a weak source? A weak source is not having that much current to feed the fault. So in the above example, we see that both are 11 kV generator, but there is a change in the impedance between the source and the line. A same fault occurring in both the cases, we find that the fault current is different. Secondly, the source voltage also is different in each case. So based on these conditions, we define a strong source and a weak source. Now let us analyze further to identify all the differences between strong source and a weak source. The left hand side, shown in green color, is a strong source and the weak source here is denoted in blue color. The first difference, you can see the impedance value We can conclude that the source impedance is less than the line impedance, or the line impedance is greater than the source impedance. This is the first difference. In the weak source, the source impedance 10 ohms is greater than the line impedance, which is 2 ohms. Or you can say the line impedance is less than the source impedance. The second difference, the fault current is very high in case of a strong source. In case of a weak source, the fault current is low. The third difference, for a strong source, the system impedance ratio is less than 1. For a weak source, the system impedance ratio is greater than 1. The fourth difference, the source voltage, you can see here, from 11 kV it has dipped down to 3.143 kV. Source voltage is suppressed, whereas in the weak source you can see from 11 kV it has just dipped down to 10 kV, so it is less affected. Whereas V2, in a strong source, this is less affected. The line voltage is less affected. From 11 kV it has moved to 7.857 kV, whereas here in the weak source it is suppressed from 11 kV to 1 kV. Now just imagine the situation of the relay. The relay works on the current and the voltage. Either it is over current or under current, or over voltage, under voltage, or with a combination of these two we can have an impedance protection relay. And here we find that the current and voltage is having a huge impact based on the impedance of the system. That is why proper setting calculation can be done only after understanding system impedance ratio principle. Not only this, it's also the location of the CTs and the PTs, because you can see V1 and V2 is just the voltage measured at different locations. So where your PT is located, where your CT is located, which CT and PT is connected to the relay has a huge impact in the protection system. So with this understanding on system impedance ratio, the protection system can be better understood. Thank you.